Hello everyone, welcome to another video of From Concept to Circuit. You are looking at the angle of arrival and the received power of the beamforming setup that we made using two ADALM-Plutos. In the TX ADALM-Pluto, we have two TX channels that are connected to two directional antennas. And in the receiver, we have two RX channels that are connected to two antennas. You can see as the TX phase being swept, you can find the pattern of the received power and also the angle of arrival and also the baseband tone that is being transmitted and received. In the previous videos, we talked about how to create beamforming at the transmitter side using ADALM-Pluto. But now in this video, we are going to expand it to also have the beamforming at the receiver side so we can further improve the efficiency of the transmission. This video talks about creating beamforming and the receiver. And then after we talked about this, in the future video, we'll go into further details of how we can align the TX and RX initially by sweeping the TX phase, and then how we can track the alignment at the RX side using different algorithms. Please stay tuned and continue watching the video as we talk about the fundamentals and show how we implemented this. Let's continue with looking at the math behind the beamforming at the RX side and how we can calculate the angle of arrival. Assuming that we have an antenna at very far distance, we can assume we have these parallel propagation planes that are reaching the RX antennas. We have RX0 and RX1 as the two antennas. And as these planes are being propagated, they first, if they are coming at an angle, for instance, in this scenario, they first reach RX1. Then as they continue propagating, they reach RX0. And the time or the phase that these plane waves are being received at RX1 and RX0 can give us some intuition of the angle of arrival. How? So assume that this plane is at the RX1 and we draw another parallel line with this plane and we name this as theta, which is the angle of arrival. The distances between the antennas RX0 and RX1, we call it D. Then based on D and theta, we can find the delta L that this plane is needed to travel after it hits RX1 until it reaches RX0. This delta L will be sine of theta multiplied by D as shown here. So then delta L is equal to D sine of theta. We call this angle of arrival. We know the D because the distances between the antennas, it's a known design parameters that we base on this, we design and distance are RX antennas. And we can find the delta L, so we can calculate the theta. How? Delta L, if we come down here, you can see that because of this delta L that the wave is propagating, it definitely when it reaches RX1 and RX0, it will have a different phase. And this different phase can be calculated by simply by how much of the lambda or the wavelength is this delta L, because the wave phase changes by 2 pi as it travels the whole wavelength, right? Its whole lambda. So the ratio of delta L over lambda determines how much phase shift we have as the wave travels from RX1 to RX0, right? And we can measure this phase shift in our ADALM-Pluto because once we receive the signal at RX1 and the mixer down mixes it to the baseband, we can find its phase because we have the quadrature information I and Q, and we can calculate the phase, right? The same for RX0. The delta here, so it's a known thing for us in ADALM-Pluto. If I want to just put lambda, which is the wave length, as c over f, c is the speed of light in when it's propagating in the vacuum, and then f is the frequency of the wave, I end up with this equation. So then, if I know if I know phi, which is the phase difference between Rx1 and Rx0, and I know D and I know the frequency, I can calculate theta, right? It's just a matter of finding the delta phi and then making an arc sign or sign the inverse sign of that equation, right? So basically, I can find theta by taking inverse sine of delta phi multiplied by c over 2 pi fd, which is here, and find theta. Also, you can do more approximation, uh, which is basically uh, if the angle of arrival is very small, the delta phi is very small, you can approximate sine or its inverse by its actual theta. For instance, sine of theta becomes equal to theta, and sine inverse of this also becomes equal to its uh, um, to this argument. So you can approximate for small angles theta to be equal to delta phi by lambda, which is c over f divided by 2 pi d. Sometimes you need to do these linearizations and assumes you have some small angle of arrivals, especially when you are creating some feedback loops, which we are going to see in the next video when we want to do some feedback loops so we can track the TX or the received wave in the RX side, meaning that in the receiver we can find the angle of arrival and then based on the angle of arrival tune the RX side so that we are kind of tracking the beam as it's received as it's being received, right? We are going to see that in the next videos, but this I just wanted to mention this linear approximation as we are as we will continue in the future. Yeah, so that's the very simple fundamentals of what's behind measuring the angle of arrival and how we can use that to have an approximation of what is the angle that the um, beam that is being transmitted is being received at the receiver. Now we are going to go look at the code and see how it's implemented inside the code and see how it works. You are looking at the code for our angle of arrival measurement. First, as always, we need to define some parameters. For instance, um, the carrier frequency, which is in this case, I set it to 2.5 gigahertz, our sample rate, or the tone that we want to send. Because as we discussed in the previous videos, because of the filter, the bandpass filter we have in the uh, in the path of ADC or DAC in the ADALM-Pluto, we cannot send 0 or 1 or any constant value. We need to, even if we want to, even if we just care about creating a 2.5 gigahertz tone, we need to create a sine wave and then use the mixer to up convert it. Because if we don't create the sine in the baseband, basically our um, band pass filter after the baseband will filter out any DC information. And that filter is actually essential because we need to clean the signal as it's after the output of the digital to analog converter, or before it goes inside the ADC in the receiver. So that's an essential thing, but it also necessitates having a tone in the baseband, generating a sine tone in the baseband, even if we want to send just a pure sine wave, high frequency sine wave at the output of the ADALM-Pluto. The other thing is I have set some variables here in the TX and RX side that basically show the TX spacing and RX spacing. Usually in the beamforming, we really need to, for good uh, beamforming, so that we don't have too many side lobes and we don't, the wave at the, especially at the TX antenna, is not wasted in other directions. We need to make sure that our spacings are close to lambda over 2, but for just um, which is here in this case will end up to be around 6 centimeter or less. But to just show some of the non-idealities of the angle of arrival, or uh, the receive power as the TX phase is being swept, I changed this to be a slightly different values. Then we need to define the number of points in the TX and RX we want to send. And also another thing is, which I'll talk as we go further into the code, is that now, because in the baseband we have a tone which I defined to be 637 kilohertz, what we end up is, so we create this, then it's up converted by the mixer, and then it's transmitted, and in the receiver, which is the second ADALM-Pluto, is down converted, and we after the ADC, we should see similar tone, which is 637 in the baseband. But the thing that happens is that it's not necessary that our RX and TX ADALM-Pluto have the exactly same frequency, the carrier frequency. There might be a slight mismatch between them, and therefore, as the receiver we receive the tone, it might not, after the ADC, it may not be exactly at 637 kilohertz. It might be at 630 kilohertz. There might be a slight frequency change. So what this means that we need to do a little more searching to make sure we pick up the correct tone. How? Basically, uh, we need to do the FFT of the received baseband data, and we know that the tone, we expect the tone around this, so we define a search window, and we make sure that we integrate around that search area, so we make sure we never miss the tone, even if it's a slightly frequency mismatched. The rest are the definitions of our um, ADALM-Pluto, which is just the IP address, the sample rate, the RF bandwidth, the enabling the channels or defining the VGA gain, and then creating the TX wave, which is the sine baseband sine tone, and then sending it. As we discussed, earlier, we basically for the TX side, we need to send two different waves in the TX side, separated by the phase that we are sweeping, which will happen as we start the sweep. I'll show later. These are some codes for the graphic, but I just want to show how we create the main thing, which is the TX beamforming and the angle of arrival. So the TX beamforming, as I mentioned, we just basically, as the TX phase is being swept, we just have a base wave, which is the main tone. We send it to the first TX channel, but the second TX channel is just we apply another phase shift to it by multiplying E by power of 1j, the phase that is currently being swept, and this creates our TX beamforming. Then this has been set in the RX side. First, we need to receive uh, the information. We need to receive the data, and then I remove the its mean from it because we are not interested in the DC region. And then we take the FFT of the signal. As I mentioned, we need to take the FFT so that we basically create a search window. And in that search window, we make sure, for instance, if we are looking at 637 kilohertz tone, we add up, if the search window is 7 kilohertz, we add up from 630 all the way to 644, so that we make sure even if there is a frequency mismatch, we'll see that received power in the receiver. Then we find the received power at the both channels and calculate the angle, the relative angle between them. One thing to note is that we need to first unwrap the phase so that it's not if it's higher or lower than um, uh, minus pi or plus pi, we don't lose it doesn't fall back uh, to minus pi and plus pi, and we actually see the raw phase information. Then what we need to do is first add the two received channels, basically because we know the relative phase difference between them. We just compensate the second channel with the minus of that relative phase, so that when we add them together, they add constructively and measure the receive power. This is the second plot that we generate. Then if I come down in the angle of arrival from that equation we saw earlier, we calculate the angle of arrival by just calculating delta phi multiplied by lambda, then 2 pi our distance, and then this will be and then we create we then take the inverse sine of um, that data. And that will give us the angle of arrival, and we plot it in the third plot. This is the whole idea and the math behind calculating the angle of arrival, creating the TX beamforming, and also adding the received powers constructively by first calculating the relative phase difference between them, then compensating them, and then adding them together. So now let's for one more time see how this will work in uh, uh, if we run it again. Now we started the code again, and we are using another mode for this final discussion, which is the log phase mode of the software. Basically, in the beginning of the video, I showed we can continuously sweep the TX phase and find the received power and the angle of arrival. And basically that is something that needs to be done in a beamforming system when both TX and RX have phased array. We need an initial alignment, and that initial alignment can be done through sweeping the TX phase to find the point that the maximum power is received, and we call that now the beam is aligned, right? And this is the mode that we are right now in. So that TX phase has been swept, and we found that 108 degree is the point that the beam is aligned. But definitely during the span of communication, the beam might get out of alignment. But now the role of tracking the beam is in the hands of RX. This can be done using different algorithms. We are going to talk about monopulse tracking in the next video, but I just want to show now that, okay, we align the beam, now we are receiving around minus 30 dB power. What happens if we change the position of Rx? And what happens to our SNR? For this SNR, this is not a very robust definition of SNR that I'm using here. Basically, what I'm doing is that I'm picking the amplitude of the main tone and then integrating the amplitude in the other regions, which can be a very wide region, and find the ratio of those to measure the SNR. That's why the SNR you're seeing here is around 6 or 7 dB, because I'm integrating for the noise part over a very large span. But this is just, I wanted to show that, demonstrate what happens to our SNR, what happens to our received power, what happens to our angle of arrival after we do the alignment and then RX moves. So let me, what I can do is that I can start um, changing the position of Rx a little bit, changing the angle of Rx a little bit. You can see the angle of arrival is now changing, the received power is changing. I can push this a little harder, for instance. You can see the angle of arrival now is ramping very quickly to a higher value. And with it, what happens is that the angle of arrival has increased, and with it, the received power has decreased. This is because our loop is open after the initial phase alignment that we did through TX phase. Now our RX is not tracking anything uh, from the TX side. We need to make sure as the position of RX is changing, we are changing with it. So we are tracking the information. We are tracking the TX beam. If I go back and change the RX position again, rotate it a little bit with respect to TX, you can see the angle of arrival now ramps down to minus 80 degree. So this definitely is working very well. We can calculate the angle of arrival. But one thing to notice is that you can see, although the angle of arrival is changing, we are not seeing a very significant change in the received power in the second plot. You can see as during the ramp, you can see there is a fluctuation, but it ramps back up again. You can see here as well, right? This is because although it's an open loop behavior, we are not doing any feedback, but for this second plot, what we are doing is that when as I showed in the code, we receive RX channel 0 and an RX channel 1, and then measure the relative phase between them, and then add them together by canceling that phase. So meaning that as long as we can calculate the difference between those channels correctly, at least in terms of power and adding the RX channels constructively, even if the RX position changes, because we are kind of doing some cancellation, we calculate the phase difference and we correct it and then add them constructively, our received power stays the same. But one thing is that this is not a very quick system. As we change as we change the behavior, as we change the distances or the angle, it doesn't react very quickly to keep the beam into the alignment. We lose for some amount, we lose the power, the beam gets out of alignment, and also uh, but after some time it gets back. What would be good is that we can react more quickly to this, so we keep um, the RX into the alignment much quicker by having some feedback loop, and also maybe as the feedback loop as the feedback loop is operating, maybe we can see, okay, now we are in the position that if the angle gets more than what we have, because we cannot measure the relative phases with more accuracy after some point, maybe we need to change the antenna uh, angle mechanically, right? We need those types of information beforehand to be sure that we do the correct adjustments. But still, this seems to be somewhat reasonable alignment happening here. We are, although we are changing the RX angle, we still can keep up with some amount, after some amount of time, we keep up with the beam. But after some time, as the phase difference becomes too much so that we cannot find the difference and correct it, we just start losing the power tracking. I don't want to pack too many information in each video, so we are going step by step. So right now we have the fundamentals of how to create beamforming in our TX, and also how to create beamforming in our RX. So now we have the understanding of beamforming, and we can approach to it both from the RX side using ADALM-Pluto and TX side. Now that we have this in our toolbox, we want to create interesting things with it. For instance, we want to see how we can track the beam with RX, as I mentioned, which I'm going to talk about in the future video. Then we want to see if we use beamforming, we can improve the communication performance we get, and also try to see what happens if we use beamforming and advanced modulations. For instance, the plan is we are going to, after we talked about these RX beamformings, first we talk about higher mode modulations, for instance, QAM, how to send them and how to receive them, how to correct them, and then first we use one antenna to do that. Then after that is done, we move to beamforming and use beamforming to do the same, and then see what happens if we align the beams and somehow we rotate RX or TX, what happens to our communication, and then we apply tracking to it and see if we can keep the similar performance of communication. These are the things that need to be done using beamforming and communication. Also, the other plan that I'm going to talk about in the future video is also we want to go touch upon a little bit about how to make radars, and how we can using this angle of arrival or using other methods find the distance from an object or finding the speed of an object in front of our ADALM-Pluto. So as always, I'm going to share the codes that I talked about in this video in our channel GitHub, and I really appreciate it if you enjoyed watching this video, subscribing to the channel, and giving a thumbs up, because it will we really need your support. Also, please comment or share this video so that we can more people get aware of our channel and we get more engagement. Thanks.